All right, so now I'll continue talking about entropy of self-shrinkers. We talked about self-shrinkers, defined them as surfaces that shrink by dilations under mean curvature flow, but we can also think of them variationally. So the idea is that we can define this functional here, the f functional, which takes as input a surface and outputs a real number. Self-shrinkers are going to be critical points of this functionals. So let's understand this functional a little bit better. So first of all, this normalization factor of 4 pi to the negative n over 2 is not very important. That's just there so that if sigma is a hyperplane going through the origin, then the value of the f functional is 1. The important part of this functional is this integral, which has this Gaussian weight. And so one should think of this as essentially computing the area of the surface, except there's this weight, and one way we can think about this weight is that there's some dust in space that is more concentrated close to the origin and is less concentrated further away, according to this Gaussian weight. And so what we're computing is how much dust is picked up on our surface. So it's essentially the area of the surface, but area closer to the origin counts more. And so what do I mean by a critical point of the functional? Well, it's a critical point in the same sense as in calculus, which is that the directional derivative of the f functional in any direction is 0. But of course, this input to this functional is surfaces, so how do we think about directional derivative for a surface? Well, we take a one-parameter family of surfaces, where the surface we're interested in is sigma 0, and we look at how the f functional changes as we go along that family of surfaces, and we want the derivative of the f functional to be 0. So if it is a critical point according to this definition and according to this theorem, then it is in fact a self-shrinker. So this gives us a way to characterize and define self-shrinkers. All right, so the value of the f functional when we're at a self-shrinker is actually important. So it's not, the f functional is not just useful to tell us what the self-shrinkers are. The actual value of the function is important too, not just its critical points. As I mentioned, it had a normalization factor so that the plane has entropy 1, there's a paper by Stone, and it's not really hard to compute what the entropies of the sphere and cylinder are, so I've written the exact values and also presented them on the number line. But what is the entropy of the Angenent torus? So this is something I numerically computed, and it is right here at 1.85. I don't expect there to be any closed form for this number, but it can be computed. And I want to also mention that there was earlier work which computed that the entropy, or proved that the entropy of the Angenent torus is less than 2. I want to say a little bit more about why we care about entropy. So entropy has implications for classifying self-shrinkers. So it's a question asked by Kolding, Minikatsi, and Peterson, and the idea is that classifying self-shrinkers is likely to be hopeless at high entropy. So I already mentioned that there are a lot of self-shrinkers that were discovered after the Angenent torus. Some of them are infinite families of self-shrinkers. So the idea is that if you allow the entropy to be high, then there are lots and lots of examples, and there's really not any hope of having any sort of classification. On the other hand, some recent results about compactness results suggest that it should be possible at low entropy. Maybe the boundary is 2. So perhaps below entropy 2 there should be relatively few self-shrinkers, and maybe we will be able to somehow classify them. Another implication of entropy is is in continuing mean curvature flow past a singularity. So if you recall the video I showed of the dumbbell shape that had this pinching neck and pinched off into 2 pieces, well, formally speaking, mean curvature flow, there's a singularity, and mean curvature flow stops there. It's no longer a smooth manifold, and its curvature is no longer defined. However, intuitively speaking, it sort of makes sense how to continue the flow. So okay, so you have that neck, it pinches off, now you have these 2 teardropped surfaces, and they will very quickly smooth out into 2 balls that will then, two spheres that will then shrink individually. And so there's some work making that intuition precise, how to continue mean curvature flow past the singularity. And in order to make those techniques work, you have to make an assumption of sufficiently low entropy. Sure, there are other ways entropy is significant, but I'm just going to list these here. So let's talk about my work in computing the entropy of the Angenent torus. So the way it works is I showed you the cross-section of the Angenent torus, so it's some sort of curve. Now we want to represent that curve approximately with a finite amount of data, so we just make lots of points along that curve. So we have a discrete curve that's approximating the continuous curve, discrete cross-section that's approximating the continuous cross-section. And then we we can evaluate the f functional on that discrete curve, and so we do the same thing. We find a critical point for this f functional restricted to this class of discrete curves, which is a finite dimensional space, and so we can compute with it. So here I'm showing what happens as we add more and more points to this discrete curve. So we can have approximate this continuous curve with 128 points, or go all the way up to 2048 points. And so we expect that as we do that, the accuracy of our computation of the critical value should increase. So we should get a more accurate computation. So let's talk about how to read this graph. So this is the entropy. I want to point out this plus 1.851 here, so this is really 1.8512, this is 1.8513, 1.8514, etc. And this is the log of the number of points, so this is 128, 256, 512, 1024, and 2048. And so at least based on this picture, it seems that as we double the number of points, the accuracy of our estimate increases by a factor of 4. So we have this value here. And so this suggests that the computed value is within 2/millionths of the true value, and then there's also later work that obtained the same value using different methods. I feel that this is very strong evidence that this is the value of the entropy, but I do want to emphasize that this is not a proof. And that there are, in fact, situations in numerical analysis where you have these very nice convergence pictures, but they're actually converging to the wrong value. Now, I would place very heavy bets that that's not what's happening here, but it does say that there is more to be done here. It's not the end of the story in terms of computing the entropy of the Angenent torus.